All right, so it feels like we're starting to reach the end of the tunnel here. What's the expression? It's the end of the road. Homework 8 out of 10. We'll talk quite a bit about the homework today, and then we'll talk about the synchronization primitives that we'll need. Mutexes, locks, same thing. Also, semaphores are the same thing, more or less. We'll find out. There's barriers we'll certainly need, and then perhaps we'll also need notification. What are they called? I think they're called condition variables. There we go. So perhaps we'll get to that as well. So the topic of this homework is correctness in a concurrent program. So we have a number of threads. There's one thread for every passenger. Right? These are elevators. Again, we have passengers are on different floors. They push a button saying where they want to go. They don't just say, I want an elevator. They say, where do I want to go? Every passenger runs as its own thread. So you could, for example, be just spinning. Every passenger could just be spinning in a loop, checking, is the elevator here yet? Is it here yet? Right? The other set of threads are the elevators. So there's some number of elevators, and they all can make their own decisions what to do when. So now we have the synchronization problem. Every elevator can only fit one passenger. So we don't want to have two passengers jump into the elevator at the same time. Then you get a violation complaint coming out of the homework. Passengers can only get on elevators when the door is open. If they walk into the door, you get a complaint. Right? They can only we should only have the door open when the elevator is there, otherwise they fall down the shaft. So things like this. Right? So there's a lot of synchronization that needs to happen. You have all these threads all wanting to do things at the same time, and we need to make sure that things don't break. So looking at the description here, there are basically two functions that you need to implement. This doesn't look right. Let's look at the template instead. So there's two files. Let's see, make this a little bigger. Oh, it's a little too big. Okay, there's two files here. There's only one that you really need to worry about. That's this homework8.c. There's also main.c. That basically draws all the pretty pictures and checks that you're not violating any constraints and actually runs things up and down, stuff like that. So maybe we'll take a brief look at that later. But for now, basically what happens is whenever a passenger pushes a button, or whenever a passenger starts, it pushes a button, then you get a call from that thread into this function here, passenger request. So this is going to be in its own thread. That thread is calling passenger request. It says which passenger is calling, right? Where are they? Where do they want to go? And then you get a couple of function pointers. And these allow you to tell the passenger to do something. So the passenger can enter. You say which floor and which door, I suppose. No. You say which passenger. Yeah, you have to identify yourself again. So you pass in which passenger, and you say which door should you go into. Or you can exit, and I think that's the same thing there. You have to specify which door and which floor. We should check that to make sure it's correct. Sorry, which passenger and which door. So here's the passenger, enter and exit. Yeah. Right. So, yeah, you have to pass those in just because we're not keeping track of everything in the back end. If you try to exit from a passenger that you weren't in, exit from an elevator that you weren't in, maybe you get a complaint as well. Okay. So passengers passing these requests. I want to go from here to there, and now so this is a little awkward, right? Most elevator controllers are not going to work like this. You probably have a single thread. You have maybe you're polling for these buttons to see if they're pushed at the moment, so everything's nice. You have no concurrency at all. that would at least make for the most reliable program. In this case, we have all these threads. So now your passenger is sitting in here. The template solution is just looping here. Right? It's waiting to get on, right? So there's just to be safe, it's a correct program already. This correct program, it grabs a lock. There's a global lock. It says, okay, I want control over, what is it that we can, let's see. I suppose occupancy and waiting, maybe, no, not that, occupancy. And I suppose you probably don't want to call these enter, I have to check that, but I don't think the enter and exit are thread safe either. So, so we say, oh, I want to be the only one doing anything right now. So then we see, okay, is the elevator on the current floor? Current floor is something that we maintain further down. Is the elevator at my floor? And is it open? And is it empty? If so, get in the elevator. Right? And then we say, occupancy, well now there's someone in there, so it's not, it can't be used anymore. So now imagine you have multiple passengers, they're all on the same floor. One of them is going to grab this lock. Right? Only one can grab it at a time. They decide to take the elevator, and then they finish this critical section. Next time, another passenger gets in there, and they see, well, they get the lock, and they see, well, the elevator, the door is still open, maybe, if you're lucky, but the elevator is full. Okay, so after you've, so here we said if we get it, we say it's set waiting to 0. So now we're looping around here until we actually get on the elevator, and then we have to wait until the elevator gets where we want to go. Right? Remember, there are no buttons inside the elevator. So now we're doing basically the same thing. Now we're sitting in the elevator, checking that light to see if it is on the right floor. If it's on the right floor, and the elevator is open, then we exit. Right. Okay. So the same thing here. So I mentioned before why I thought that this template solution was running so slow. I said, well, maybe I had a little sleep in there. That's not the case. It's just a bad solution. So this solution, it goes to every floor and opens the door. And then it closes the door, and it goes to the next floor, opens the door, and so on. Right? And it takes a little while. It takes a little while to open and close the door. There's delays in the main here. Actually, let's take a look at that. Door open. Hello. Oh, it's not. It's called elevator. Door open, maybe. Come on. Elevator open door. Oh, instead of door open. Okay. All right, so you see what happens here? It's a little sleep before we return. So we set everything, and then we sleep for a little while before we let the elevator do anything again. Okay, so this elevator, this is actually same thing. You don't really see the thread. The threads start up, but the elevator, whenever it's ready for a new decision, it calls elevator ready. And now it's up to you to tell the elevator what to do. So we do the same thing here. We say we want to be the only ones playing with this, in this case, the state. So we have a shared lock. Maybe that's good, maybe not. That's probably not what's slowing things down too much. So now if the elevator has arrived, well, then we open the door. Right. If the elevator is open and the elevator says I'm ready, right, then it's time to do something else. Then we probably close the door. Okay, and then if it's neither arrived or open, now we're in transit. So now we need to decide where to go next. So we're probably close the door and we want to go up, or we want to go down. So what this thing is doing here, like the direction multiplied by -1 here, we're just saying, okay, keep going up until we get to the top. If we're at the top, change direction, start going down one at a time. Right? Get to the bottom, we go up. So a really dumb solution. Yeah, you know the question?
Yeah, so in the above function, those would be the passenger thread in this function, and this function is the elevator thread.
Exactly. And so, yeah, so you never have passengers calling this one, you never have elevators calling the other one. So there's a tricky bit here. I don't know if we saw that. Maybe we can see it. Let's run this. The program is correct in the sense that no passenger dies or even bumps their head, but and they eventually get where they want to. But it goes really slow, and sometimes they even miss an elevator. Let's see here.
Do you need that sleep when you're opening the door? Closing the door?
Oh, you're not allowed to change main. Let's see.
Okay.
So this is sort of a simulator, right? So main.c is just saying, okay, you can't just go like that, right? That you could be if that was possible, it would be pretty efficient to stop at every open, close, and go, right? Of course, your passengers would probably get squished, right? So, okay. What's this? Yeah. 8. Yeah, okay. So what I was showing you last time, it was actually the template for we used the same homework in 385 before. Okay, so look at this guy. He wanted to go to 0. Okay, that was good. Maybe there was some. No, he still wants to go to 0. Look at that. So he's trying to get to 0. Of course, the elevator doesn't care, so it goes up and down. Let's see if he gets off this time. Yes. All right. So someone wanted to go to 3, and apparently at 3 there was another one that wanted to go to 0, it seems like. Or? Okay, so now on number 1 there was a 25. When it goes to 25, we'll pick up the next one at 25. At 26 there was one that wanted to go to 5. Okay, so let's see. Does it get up to 5? Most of the time it seems to work.
My machine, no.
Yeah, every now and then it's gonna miss. It depends a little bit on the scheduler. So I'm running this on OS X now. It'll be slightly different from on Linux. But every now and then I think you'll probably see it not manage. Anyway, so you see how this is stupid, right? You get to number 1 here, to floor 1, it says I want to go down. So then we go all the way up and we open the door on every floor and no one can get in. So we clearly need to change that. And then there's 3 more elevators and we ignore those. So,
There's someone at 16 that wants to go to 16.
oh, well that should be easy.
Will they grab them and go all the way back up and all the way back down?
I don't know, I guess we'll find out. So 14, we're going to get to 14, and then it'll take the 16, let's see if we...
Yeah.
Oh.
Yeah. Takes them off. We just want to go for a ride. Isn't it?
Okay. Yeah. Okay, so why is it that we only are running 1 elevator here? Well, it says if the elevator is at number 0, then we don't do anything. Right? So it's actually, the elevator keeps coming back, probably, saying, I'm ready, let's go. And we just ignore it. Okay, so I think that's about it for the setup. Now, what are the challenges here? Well, first there's this problem of people missing their elevator. All right, so that didn't happen very much in the demonstration here. That's too bad. Maybe we can see it once. So we really need the elevator to wait, right? The elevator knows that there's someone there. So the elevator ought to open the doors and wait until the passenger gets in, and then close the doors, right? So we can't really do that well with locks. Locks, they let us make sure that only one at a time get to access something. But it's not a good mechanism for waiting. So what you can do is you can spin, right? You can have a variable that says, oh, I'm inside, right? Passenger inside. We have a variable there. And then you have an elevator that checks that variable spins around and around and around and checks that variable, and you have the passenger. Once it gets inside, it sets the variable, and now you're good. In fact, you don't even need a lock for this. But then you have this elevator spinning, and that's going to use a lot of CPU. In fact, I think there was a CPU requirement on here on performance. Right. So you can do all of this, much of this with spinning, but you're not going to manage this 10% of the CPU. You know, it strikes me now that you all have Amazon instances with a single core. Run it locally if you have a Linux machine. If you don't have a Linux machine, we're going to have to hook you up with multi-core Amazon instances. That's the only way, I think. Okay, so your program, I mean, you can start working on your program now. There's no question about that. But in order to really see if it's working, you're going to need a multi-core machine because there's different synchronization challenges there. So yeah, I'll probably just make one for everyone, and then that'll be that. Okay. Right. So that brings us to the next problem here. How do you get this other kind of synchronization, the waiting, to work properly? So there's two mechanisms for this. Let's see. So synchronization primitives. The main one, and the one that really matters everywhere for everything, is mutual exclusion, or lock, also called a semaphore. A semaphore is ever so slightly different, but for now, let's just think of them as the same thing. In fact, a semaphore can be used to implement other things as well. Okay. The next one that we need to know about is condition variable. So what are the operations on a mutual exclusion lock? It's so in pthreads, is it just mutex lock, right? And then pthread mutex unlock. And what's nice about that is anything in between here, only one thread can execute per lock. So we should point out again here that the lock has nothing to do with whatever you're doing in here. It's not associated with any kind of data. Maybe if you've done a little bit of Java programming, you know, or the synchronize keyword, that means you have a lock that's associated with every object. That's not the case here. We have you can make a lock and it means just anything. And so I think this bathroom thing is still a reasonable approximation right now. Once we start having two locks, the bathroom analogy doesn't work anymore. Completely broken. Okay, so next, a condition variable lets you wait and notify. So wait blocks until the variable is notified, and notify sends notification to waiting thread. Okay, so how could this be handy? Well, in the elevator case, you can make a condition variable for the elevator. Well, you can call it passenger inside, perhaps. And we'll have the elevator wait for passenger inside, and then when the passenger gets inside, it can notify that same variable, and now the elevator wakes up. Pretty handy. But in our case, it doesn't quite cut it. Because if you notify if you notify a variable that no one's waiting on, nothing happens. So now imagine the following situation. Your elevator comes, your elevator starts running, right? Starts opening the door. The passenger, on its own, notices that the door is open and gets in, right? And then notifies. And now the elevator starts waiting on the passenger inside variable. What happens? It's never going to get another notification. So it'll just wait forever. This could be considered a deadlock. Okay, so this is a little hairy. Notification are lost if no one is listening. So you could imagine then having another condition variable, right? But it becomes this kind of pile of weird, it doesn't really work. It makes for very, very complicated programs. So most of the time, or at least certainly in this homework, you're probably not going to want to use condition variables. They can make for a very efficient program if you get it right, but they're a little bit complicated. The final one is barriers. Barriers are really handy. So here you can initialize with a size. So you say, well, okay, there's just a size. And then you can wait on a barrier. So now the wait is going to happen forever until there's enough people waiting on this barrier. Right? So let's see, how would that work? Yeah. So imagine you have this wall. It's kind of a poorly built wall, and you try to push it over so you can get past, but you can't do it. Right? So you keep pushing, but that's the waiting. And now someone else comes, and when enough people are there pushing, eventually it'll fall over. Right? So same thing here. That's the enough people. How good is this barrier? How strong is it? When enough people are waiting, pushing, eventually it'll fall over, and then they can just go. And there's no order in which they will go, so it'll block until size threads are waiting. So this is really handy in the elevator homework, because now you can make a barrier for every elevator. Let's say you can have a barrier for 2. So when the elevator opens the door, you can wait for the barrier, and a passenger comes, gets inside, it also waits for the barrier, and now the elevator can close the door and go. Right? So that's one handy way of writing this. Barriers are really easy to work with compared to condition variables for sure, and even sometimes compared to mutexes. But they're not. They can't replace a mutex. So for all of these, it's true that you don't really know what order things are going to happen in. So when you lock something, it'll wait until you grab the lock, right? It'll wait forever until you grab the lock. So now you have a bunch of threads that are all waiting on a lock. One of them is going to get it, but you don't know which one. Just any one. So what could happen in the elevator case? Is it still running? No. What could happen here is that the elevator grabs the lock because it's wanting to move, and it grabs the lock, and then releases the lock, and then tries to grab the lock again, and it'll just get it again. Yeah.
I thought locks were queuing.
No, not by default at least. There are queuing locks, or ordered locks is what they're called. But a pthreads mutex is not, unfortunately. It would be handy. Any reason why? Can you think of a reason why it wouldn't be like that? Why is it not a queue?
Someone has to keep track of it.
So why doesn't someone keep track of it? Well, you could imagine this being just part of the pthreads library, whatever. Locks need to be fast. We want them to be as simple as possible at all, because you want to be able to have a very short critical section. Just grab it, update that variable, get out. So now, if it suddenly becomes a complicated queuing situation, it's probably not worth it in the end. Sometimes it's really important, and then you'll use an ordered lock. All right. What's our question? So let's think about how a lock might be implemented. Implementation of a lock. A mutual, a lock. Okay, so what's the deal here, right? We probably need a variable that says, is the lock taken? And if the lock's taken, well, then we can't go. But if it's not, then we take it, and then we go. Right? So that seems easy. So we have a Boolean for every lock, right? We have a Boolean taken, and then we have some kind of condition saying if taken, then, oh no, we can go like this. Oh, that's not good. Let's try this first. If taken, then return. All right, and then, or maybe otherwise, we'll say taken equals 1 equals yes, true, return. This is really ugly. Okay, so imagine here, this is sort of a class definition here, right? So we have a member variable taken, and this is what you call on this lock. That's not exactly how it works in T-threads, but that's fine. Problems? Yeah, so that's our first problem here. We're supposed to block. This doesn't seem like it's blocking very much. It's just returning whether it's taken or not. So it's not going to make any mutual exclusion happen here. Okay, so why don't we go while taken? We go like this instead. Oh. Alright, so now this function is blocking. It'll keep looping here until that it's not taken anymore, and then you take it and you return. Oh, yeah, okay. So this will burn a lot of CPU, but there's two kinds of locks. One is called a spin lock. Two principal kinds of locks. One is called a spin lock, and one is like it's called a semaphore, but that has nothing to do with semaphore. So it's a sort of an OS scheduler-based lock, where the OS puts the whole thread to sleep, and you go in this queue and all this stuff. But what you usually end up using is a spin lock. And it's safe, it's okay, because you expect critical sections to be short. So whoever's holding the lock right now, they're not going to hold it for very long. Maybe they'll hold it for 100 instructions, and then they'll set taken to false, and then you get to go. So now the question is, do I want to go through all the trouble of doing a system call here, getting the OS to suspend my process, save all my state away, and so on and so forth, only to wake up a few hundred instructions later? It's not worth it. So you don't really have much of a choice. You're going to have to spin, at least for a little while, to see if it comes back quickly. And then if you spin for a really long time, you see this guy, he's taking forever. And then maybe you go ask the OS for help.
But you might end up spinning for a long time if there's a lot of threads waiting.
That's true. So if there's really a lot of lock contention, a lot of threads all wanting this lock, then most of them will be waiting and they will be spinning. So the question is, I suppose, what is the better solution? So now if if they're all short, so now you have, say, 10 threads, and they're all doing short critical sections. The lock is always busy, and they're always waiting for this lock. Still going out to the scheduler, using 10,000 instructions or 100,000 instructions to get that right, it's not going to be more efficient. Yeah, you're burning some CPU here, but you have to wait anyway. So the fastest way to get back is probably to just sit there and wait. Spin locks, they look really ridiculous, but they're not as bad as they look. There's another reason why they're not so bad, I suppose. That's, all of this is going to be sitting in a cache. So you're not going out to main memory. So you're just doing a little spin, looking at your cache lines. It'll probably be kind of power efficient compared to using the entire memory system. Okay, anyway, so it seems like we're blocking here, and then eventually we run, and now we have the lock. And then we need, of course, the unlock. Looks the same. No, it doesn't look the same at all. It says unlock taken equals false. That's all there is to it. So if you look at this, it seems like we already have that property with the ordering isn't known, right? Because everyone's running this loop here. And one of them's going to find out first, and then they will get to go. And we don't know who that is. There's no ordering in this loop. Because they don't even know how many else are waiting, if anyone else is waiting. Okay, but there's a problem. There's an enormous problem in this code.
What if two people read at the same time and they for both of them taking is false? So now they go in.
Exactly. So we have a non-atomic operation here. We're first checking, and then we're setting a value. This sounds familiar. We were just doing this with I++. There we're doing three things. Reading, updating, writing. Here we're just reading and then writing a different value, but it's almost the same thing. So it's two operations, and we don't know the order in which, or we know for this thread they will come in this order, but you might have another thread running at the same time, both checking taken, and then both saying taken is true. That's fine. Then it's taken, right? Or? No, it's not fine because they will both return. So now they're both in the same critical section. The lock didn't work. Any ideas?
Is there a way to use atomic operations for that?
Use atomic operations.
Is there a way
You need a special atomic operation. It's called test and set, or sometimes it's called a swap. And modern CPUs all have it. There is actually one solution. It's called Peterson's solution. If you have only two threads, or maybe it could handle three. I think it was only two threads. And you have a bunch of different variables that you're updating, some counts that you're updating, and two counts agree, something like that. You could actually make a mutex without an atomic operation for two threads, I believe. I don't think that's in this book, but it's in some other books. But any practical implementation has to use atomic operations in the CPU. So let's see if we can find something about that. Test and set. Okay, that's pretty good. Actually, I was thinking maybe we want to dig into the pthreads implementation of this, but maybe not. What do you think? Are you interested? Do we want to find out which opcode are we using to implement a mutex lock in pthreads?
I assume it's a test.
You assume it's a test and set. Well, I'm not so sure. There's a few different ones. Okay, let's have a vote. Yes, no. Yes, no. Okay, lots of people indifferent. All right, good. So let's see if we can figure that out. So we're going to want to disassemble. Let's see. Let's go on Linux. So what do we have? We will need to find our libp threads. It's probably in. Oh no. Okay. Not there. Well, we had a program here. This is using threads mutual exclusion, right? Join here mutex lock. Okay, good. So we'll just compile that and disassemble it and see what comes out. What's that? Okay. Oh, I'm sorry. Wrong screen. Yeah. Okay. So yeah, I was just thinking this threads.c. This is doing some mutual exclusion. So if we compile this static on the Linux machine, that seems like an easy way to just get the code so we can look at it. So we'll copy that to my Linux machine. Oh, it's like that, I think. Ah, there it is. Okay, that was easy. Yes. All right, so what did I do? Compile with static. So now we're not using any libraries anymore, right? We're going to pull in all those dynamic libraries into our binary instead. And then I linked with pthread. It wasn't happy if I wasn't linking with pthreads, and I get all this undefined reference to some functions. Okay, so now we can disassemble, presumably. Actually, what did it look like? Here, tfunc has a mutex lock. So let's see what it's actually calling, but there ought to be a mutex lock. Tfunc. Right, pthread mutex lock. Okay, so we'll disassemble that. There it is. Must be, because that looks really funky. All right, so on the Intel architecture, there's a few of these atomic operations. This one says compare values and then exchange. So if it's, let's see, I think it is if they are not the same. So if my EDI is not the same as whatever is specified over here at this address, then we switch them. If they are the same, then we say, okay, they were the same, so then we have to try again. Yeah.
Which generation of processors are having this instruction?
Beats me, but it's not going to be very young. It's probably been around since maybe 386 or something. Or maybe not. Maybe Test and Set was doing it for a while. But either way. So there's actually two versions of this compare and exchange. You can specify which one you want with this lock here. If you don't specify lock, what does it do? Well, it compares the two and then exchanges the value. But it's not. It doesn't care about other processors, other cores. If you say lock, now it's going to hold on to this cache line and tells all the other, before it does anything, it tells all the other cores that this address, these 64 bytes, don't touch them. Right? So now this is implemented in hardware now. It doesn't know anything about the actual values or what's in those 64 bytes, but it says this cache line is mine for the duration of this instruction. So now it's able to both compare the value and then write the value, and then it releases the lock. So in the end, it's only worked because there was a hardware implementation of lock, right? So unfortunately, that's pretty much how it is. You're gonna need some way that all these things can coordinate, and it's much easier if you have wires. Some wires just flip that switch, and now no one does anything until you flipped it again. In fact, I don't think they take it quite that far. They don't stop all the other cores. They just say, if you try to touch this cache line, it's a no-no.
This atomic operation is only available within pthread library, or is it in the C library as well? Or is there
Okay, question is, are these atomic operations available only in the pthread library? That doesn't make much sense. All right.
Well, why is it called pthread? Oh, it's used in
So the implementation.
the mutex lock. Right?
Yeah, exactly. So we're looking at the mutex lock here. You can't implement pthread's mutex lock without an atomic instruction, and it's right there. So, in fact, let's look at mutex lock. Oh, that's ugly. What did it do? Yeah. Okay, so what are we talking about here? 77 bytes so far. 174, 200. Okay. Here's another one, apparently. Oh, it checks all sorts of little things here. So, you see, even this lock, which is going to be very efficient, very good. The number of instructions is 447. No, I don't expect that you always have to, sorry, the number of bytes run is 447. I don't expect that you always have to do that. Right? Much of the time, it'll work out nicely in the very beginning. You grab it and you go. Let's see if there was anything more really interesting here. It scrolls kind of poorly today. Oh. Yeah, so that seems relevant. See that? SMP, anyone know what that means? Symmetric multiprocessing. So it says, is there more than one core in this machine? I believe. Or maybe it says, is there more than one chip? Could be one of those two. So it probably does things different depending on the how this pthread was compiled, or what we're running at the moment, what machine we're running on at the moment.
So there are atomic operations of machines with just a single core. That would be good.
Yeah, there are atomic operations. Almost every operation is atomic, right? Every store and add and all of that. Here you have an atomic two-step operation. You have a read and a compare and a write. 3 steps, actually. But yeah, I wonder if those are even implemented on a single core machine. Maybe for compatibility. It doesn't make any sense. Certainly wouldn't be expensive. So it turns out that those instructions like these, the locking ones, they're actually quite expensive. So the reason being that when you try to run this, the CPU is going to has to tell all the other cores that, okay, I want to get this lock now. The cores have to agree that he's going to get it, and then you can start running again. So now there's communication possibly across these copper lines on the board even, right, between the CPUs. So that adds quite a lot of overhead. So it's not cheap to do these operations. Okay, so those are our locks. So we can't say while taken true. We'll have to do say while test and set taken true. That's all. All right. So now, if taken is true, this returns false, and so we will do it again. Oh, it returns true. Sorry. They're equal, so it returns. Let's see how they go. Yeah. If they're equal, it returns true, so then we do it again and again and again. And eventually, it's not true anymore. Then we switch the two. In this case, test and set. I said, what was it? It wasn't. It was compare and. What was the? Compare and exchange. Yeah. Compare and exchange. All right. So if they're not equal, then we get the value. Doesn't quite work, I think. It's true here isn't any good. We want to get the value of the taken into there. You can't assign something to true. So. Anyway, so now we're able to do this for a single thread, and we have a proper lock implementation. Okay, so What about if you have, if we want to do this in the OS setting? So now this is a spin lock. Sometimes you're going to have very long running things. Say you want to, what would be a good example? Nah, I don't have a good example. We'll leave the semaphores for next time. We don't need them much anyway. Okay, so what about a barrier? How would you implement a barrier?
Keep account of how many threads you're putting to sleep for that barrier. Would you have to put them to sleep?
Let's try this out.
I guess you could just spin. Yeah, you could just slip into the letter.
So int size, I suppose. Count. Okay, so now we have a weight. So we'll say perhaps count plus plus, right? Because there's one more weighting. And then what? Well, count is less than size. Okay.
But the count plus plus has to be atomic.
Yeah, this doesn't look very good so far. Okay, so to make the count thing work, we have to at least say lock and then unlock. So barrier lock.
Why does the count be atomic?
Why does it? Oh, it needs to be in a critical section because count plus plus is not an atomic operation, right? And that doesn't exist in the. So the Intel architecture may have a few atomic operations built in. They don't have an atomic increment, as far as I know. As far as I know, I mean that might have been added later. Who knows? Okay, so we're. Is that good enough? We need a return? Okay, fine. I mean, it'll return anyway. Yeah, so now we have a little bit of a problem. It looks fine, but this is going to be spinning potentially for a very long time. Right? So with a mutex, we're trying to protect a critical section. Someone else is in the critical section. They're count plus plusing. They're not going to be count plus plusing for very long. So it's okay for us to have this spin lock around that critical section. For the barrier, this is a passenger here who has pushed the button. And he basically needs to wait until the door opens. Right? And there's 100 other passengers, and there's one elevator, and they keep going up and down, right? It's no good. So we don't know, for a barrier, there's no reason to believe that there's going to be a short wait. So for that, we need to put the whole thread to sleep. You could, perhaps you could spin for a little while. Like you could spin 10,000 cycles, just in case. Right? But then after that, you're going to have to ask the OS to put you to sleep so that you don't burn the CPU while you're waiting. So we'll talk about how that's done next time. Questions on the homework?
Are you saying that we're making each elevator on a separate thread, or just all the threads working on the elevator?
Yeah, okay, so
like 16 threads working on one elevator.
Look at this here. The beginning of this whole thing says pthread create, one for every passenger, one for every elevator.
Okay, that makes sense.
And then it's calling start elevator and all this stuff is going on there. There's one more thing I wanted to show you here. When you're testing things out, This is a kind of a fancy makefile. Oh, damn it. Hey, that's what happens with Emacs. That's weird stuff sometimes. Okay, so here, see, I'm passing in all these defines. I didn't have to do it this way, but I decided to do it that way. Okay, so these arrive as macros inside of the program. Just like you said, define delay equals 10,000.
You can use that now.
So now,
Just delay now in the program.
you are not supposed to change the makefile. I mean, we'll use our own makefile when we're trying things out.
Right, I mean, in the
But-
program now you can use delay.
Yeah, exactly. It appears as a macro, as just a predefined preprocessor macro. So anyway, you see the test here. It runs 3 different situations, all with a certain delay. This is just so you can watch it and it looks reasonable. Burn-in, this is a really big one here. This is handy to run in case you're worried that you have a consistency problem. Right, here it runs very quickly, very small delay. It has 100 passengers. Every passenger goes for 100 trips, and there's 10 elevators and there's 40 floors. It's a nuts, really nuts sort of test. But if you pass that, you're probably in good shape. Okay, so yeah, try passing in some other parameters too, and you'll see how it runs.
You should say make burn-in.
Yeah, you just say make burn-in and it'll do it. In fact, I'll do it now. No, I'm not going to do it now. All right. See you Friday. And it's office hours at 1 p.m. in my office.